All right, this is section 1.5, and we are going to be looking at the transformations of functions. And in this section, we're going to look at a few parent graphs. That means the most basic version of various types of functions. And then we're going to look at how we can shift those graphs. And below each of the graphs, you'll see some basic information about these functions. As we shift the graphs, that information may change a bit. But let's look at our first one. So we have a constant function. This is maybe something like y equals 2 or something like that. This is a function where we have y equals a number or f of x is equal to a number. And it's just a horizontal line. Those are called constant functions. The next one is the identity function. This is just a straight line y equals x or f of x equals x. In general, these are called linear functions where we just have a straight line. The next one would be an absolute value function where we have the absolute value of x. This is a sharp V. It meets at a point here. And then we have these straight lines coming straight out from that vertex. Great. The next one will be our standard quadratic function. The shape is called a parabola, and we have this like curved U here, and it meets here at a vertex at the origin. But again, if we shift the graph or change it, it might not be at the origin. Then we have the square root of x, and this is this kind of curved graph coming this way. It's not defined where we're looking at negative x values. Then we have x cubed, and this is this kind of curved graph. This one can change quite a bit. Depending on how we change the x cubed function, it can go down, up, and then down. It might not share this exact same shape. And then we have the cube root of x. So this is the most basic cube root of x function. It is defined where x values are negative because we can take the cube root of a negative number. So on to how we can shift our graph. If we have a number added onto the end, then that means my graph is shifting up. If we have a number subtracted on the end, that means my graph is shifting down. If I have something subtracted on the inside, it's actually the opposite of what you think. It is moving to the right in a positive direction. And then if you have something added on the inside, it's actually moving to the left in a negative direction. If we multiply by something out front of the function, that is a vertical stretch or shrink. If the absolute value of that number is greater than 1, then it's stretching or getting taller. If the absolute value is less than 1, it's shrinking or getting shorter. We can also stretch and shrink horizontally, and we can also do some reflections. So let's first take a look at reflecting across the x-axis here. So if I have a negative out front on my function, if this were my original function and I multiplied by a negative out front, then it would reflect across the x-axis. Reflecting across the y-axis is having a negative on the inside. So notice the difference here where it's on the outside or inside the function. If it's on the inside, it's reflecting across the y-axis. So if this was my original, then this would be the reflection. Horizontal stretching and shrinking is also kind of the opposite of what you would think. If your C value is greater than 1, or in other words, the C value, absolute value of it, then this is going to be a shrinking of our graph. It's actually going to get tighter or smaller. If you have a C value between 0 and 1, so a fraction or a decimal, then it's actually going to be stretching and getting longer. Okay. And this next chart on this page is really just a summary of all of those shifts and shrinking and all of that that we just went through. So now that we've kind of talked through all of them, let's see them in action in some examples here. I have the square root of x, and we want to graph the parent function and the transformation. So I have my parent function. We're going to call that y equals the square root of x. And we saw that graph a few pages before and saw what it looks like. Now, what you can do is you can still make a table of points if that's helpful for you, and we can plug in some values. Well, I know I can't plug in anything negative here, so I'm going to start with 0 and then 1, 2, and actually, you know what? I'm not going to use 2, and I'll tell you why. I want to plug in something I know the square root of, and 2 is not a nice number to take the square root of, but 4 is. So I'm going to plug these values into the parent function, and I get the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. And now I can plot those points. So 0, 0, 1, 1, 4, 2. And I can see the shape of that graph. Now, the shift here, this -3 on the end, means that all of those points are moving down 3. So rather than making another table, all I need to do is shift each one of those points down 3. And that gives me the translated graph g of x. Okay. Let's see another example of this. If we have the absolute value of x plus 1 and -2, my parent function is, and I'm going to use y again, y equals the absolute value of x. So again, if I wanted to, I could make a table and I could plug in, let's say, -2, -1, 0, 1, and 2. We can plug negative values in here. And if I plug in -2, the absolute value of -2 is 2. The absolute value of -1 is 1. Absolute value of 0 is 0. Absolute value of 1 is 1. Absolute value of 2 is 2. And I can plot those points. -2, 2. -1, 1. 0, 0. 1, 1. And 2, 2. And I can draw my graph that way. And this is y. And then I can graph h of x, and this +1, again, this inside shift is the horizontal shift, and it's the opposite of what we would think. So this is going to shift my graph to the left 1. And then this -2 is going to shift my graph to down 2. So all of these points, and a lot of times I'll start with the vertex here, actually, not like left to right. Start with the vertex is going to move left 1 and down 2. 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 And we can see that shifted graph. And that is h of x. Taking a look at the next one, we are looking at a parabola, and I have my parent graph, y equals x squared. But rather than just using x squared, what I'm actually going to do here is use -2x squared. And the reason I'm going to include that -2 is because then the shifting I'm going to do is just taking these into consideration. So that +2 means I'm going to move left 2, and that +1 means I'm going to move up 1. So I'm going to make my table using this graph that includes that -2. The negative will flip it over, so my parabola is going down, and then that 2 will stretch it by a factor of 2. I'm going to plug in -2, -1, 0, 1, and 2. And I'm picking these values. Those are not given to me anywhere. You can pick whatever values you want. I always like starting around 0 and picking a couple on each side as long as the function is defined in both of those directions. -2 squared is 4. 4 times -2 is -8. -1 squared is +1. +1 times -2 is -2. 0 squared is 0 times -2 is also 0. 1 squared is 1 times -2 is -2. And 2 squared is 4 times -2 is -8. So we have some points that we can plot. 4, 6, 8. And draw that, not quite a parent graph, but this graph we're going to start with here, y. And then we're going to shift everything left 2 and up 1. 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 And that gives me my new function, and this is f of x. Okay. Now the next example, we have -1/4 x cubed. I'm actually, with this one, because there's no shifting up, down, left, or right, I'm going to go straight to the answer. I'm not even going to um, uh, like use a parent graph or anything like that. I'm going to use x and g of x. However, I am going to pick values that work out nicely because I have a 1/4 here, and I'd like to pick values that don't give me any ugly fractions. So I'm going to pick, let me give myself some space here, 0. I am going to pick -1 and 1. And then I'm also going to pick, let's see, you know what? I'm not going to choose -1. Change my mind. I'm going to use -4, -2, 2, and 4. And again, I'm choosing these values because I want numbers that are going to be divisible by 4. So if I plug in -4, -4 cubed is -64. -64 times -1/4 is +16. If I plug in -2, -2 cubed is -8. -8 times -1/4 is -2. 0 cubed is 0 times -1/4 is still 0. 2 cubed is 8 times -1/4 is, you know what? Oops, this is +2. -2. And then 4 cubed is 64 times -1/4 is -16. So I can plot those points. I'm actually not going to do the 16s because they're off the graph here, but I will do the other points. I have 0, 0. I have -2, 2, and +2, -2. Now it could look like this just goes in a straight line, but because we went over those parent graphs, we know the shape of x cubed. So it has this kind of curve to it that's pretty steep here, and this is g of x. So we're not doing anything crazy here. We're still using the point plotting method to plot these graphs. There is one more topic in this section that we're going to go over, but it is not a graphing topic, but it is tied to graphing. And what we're doing in this section, and really all of chapter 1, is collecting clues for looking at polynomial functions. Chapter 2, we're going to start looking at some more graphing. And then chapter 3, we're really going to get into graphing polynomial functions and how to use those tools. So here I have the definition of even and odd functions. Even functions follow this property here. If you find f of -x, I plug in -x everywhere there's an x. That's going to be equal to f of x. And what this means is that it has y-axis symmetry, meaning it looks exactly the same on one side of the y-axis as it does on the other. And then this function, odd functions, have this property here. If I have f of -x, it's going to equal f of x times -1. And this has origin symmetry. It's reflected across the line y equals x. So these give us clues about what the graph looks like that we're going to bring back in chapter 3 and use to graph polynomials. So this first example here, we have f of x is equal to x cubed minus 6x. Anytime you are checking for what kind of function it is, if it's even, odd, or neither one of those, that is also an option. You first want to check for if it's even. So first we're going to find f of -x. So wherever I have an x, I'm plugging in -x. And -x cubed is -x cubed. And then -x times -6 is +6x. And this is not exactly the same as the original function. So it's definitely not even. But what I can check next, again, if we had f of -x, that would be equal to the original, but it's not, so it's definitely not an even function. But next I can check, okay, f of -x, is that equal to the original function times -1? So next I want to find, well, what would negative f of x be? So -1 times x cubed minus 6x. Well, when I distribute that -1, I get -x cubed plus 6x. And those are, in fact, equal. F of negative x is equal to negative f of x. So what that means is that this is an odd function. Okay. So if this were a quiz or an exam problem, all of this work and the conclusion that it's odd is the answer. It's not like just writing the word is your answer. The next example here, we have g of x. And again, first I want to check, okay, is it even? So I'm going to find f of negative x. Well, f of negative x, if I have that, then I'm going to go ahead and take my original function, power minus 2 squared, and I'm plugging in negative x. Negative x to the fourth power is x to the fourth power. And then negative x squared is x squared times negative 2 is negative 2x squared. And this is exactly the same as the original function, which means that this is even. And lastly, we have x squared plus 2x plus 1. First, I'm going to look to see if it is even. And so I have negative x squared plus 2 times negative x plus 1. And that gives me x squared minus 2x plus 1. Almost exactly the same as the original, but this one sign change is what's throwing it off. So it's not even. Then I'm going to find, well, what's negative h of x? So negative h of x is negative 1 times x squared plus 2x plus 1. And distributing that negative 1, I get negative x squared minus 2x minus 1. And since those two are not the same, it's definitely not odd. So it's not even, it's not odd, it's neither. Okay. And that brings us to the end of section 5.